As the title suggests, this video will provide information and training needed to work safely with nuclear gauges. But before going into safety, just what is a nuclear gauge? For our purposes, we'll use the term gauge or nuclear gauge to describe devices which use radiation to measure the level or density of a material during industrial processing. These devices normally consist of a source by defining radiation as energy traveling through space in the form of particles or waves. Wave-like radiation can take the form of familiar things like light or heat, or less familiar things, laser beams or microwaves, X-rays from the machine at the doctor's office, or gamma rays from radioactive materials. All of these are examples of electromagnetic radiation, which differ only in the amount of energy carried by each ray or photon. Back in high school, we learned that an atom contains a compact nucleus made of protons and neutrons, and that this core is surrounded by a swarm of orbiting particles called electrons. Viewed by something much smaller than the atom, it might look like a solar system, made up mostly of empty space. On this scale, solid objects don't look so solid. The penetrating and ionizing properties of X and gamma rays are a dual-edged sword. These properties make them useful and cause them to be potentially hazardous. The penetrating property was first noticed by Wilhelm Röntgen when he discovered X-rays in 1895. He found that this new radiation passed easily through air and lightweight materials. To understand how, let's take a closer look at the human body as a biological system. The human body is composed of trillions of individual cells, made up of a variety of different kinds of molecules. The molecules can be as small as 2 atoms or as large as millions of atoms. Either way, the atoms are held together by chemical bonds. Chemical bonds are formed when the individual atoms share their orbital electrons. As we've seen, ionizing radiation can eject electrons from atoms. If the ejected electron was being shared in a bond between 2 atoms, then its removal would break the chemical bond and the molecule would come apart. At this point, it's important to understand that you don't have to work with nuclear gauges or be X-rayed at the doctor's office to be exposed to ionizing radiation. We are all being exposed to this type of radiation all the time. We ourselves are measurably radioactive as a result of taking in small amounts of radioactive materials all during our lives. The radiation exposure we receive from these natural sources is called natural background radiation and is a continual source of exposure to everyone on the planet. So just how much exposure do we get from natural background radiation? Radiation exposures are commonly measured using a unit called a millirem. 1 millirem is a small amount of exposure and is about equal to the dose we all get each day from background radiation. How does this compare to exposure on the job? In addition to background radiation, the average radiation worker in the nuclear power industry gets about 300 millirem per year, while it is estimated that the average gauge user gets only about 30 millirem. These average doses are well below the annual dose limit for radiation workers, which is 5,000 millirem. Now that we have some perspective, let's talk about high-dose effects. However, to minimize this risk, many governments around the world have adopted a policy of ALARA regarding exposure to ionizing radiation. ALARA stands for as low as reasonably achievable. Under this policy, all exposures must be kept as far below the dose limits as practical, and unnecessary exposures must be avoided. Factors used to reduce worker exposures decay rates are measured in units of disintegrations per second. A disintegration is said to have occurred when the nucleus of a radioactive atom expels its excess energy in the form of particles or waves, or both. One unit used to measure source size or strength is the Curie. Once the source strength has been determined, the expected radiation levels and projected worker doses can be easily calculated. If the calculated doses are too high, steps can be taken to reduce the dose to the workers before any actual exposure Common occurs. Administrative controls include quantity limits set by state or federal regulators, assignment of a radiation safety officer responsible for all activities involving radioactive materials, prior approval of planned work involving radioactive materials. If your job involves routine exposure to radiation, you are considered a radiation worker. If your job doesn't involve routinely working with radiation, but you work at or visit locations where radioactive materials or X-ray machines are used, you are considered to be a member of the public. You can be confident that if you follow these simple precautions, your exposures will be well below those known to cause any harmful effects, while you and your company enjoy the full benefits of working safely with nuclear gauges.